The closest star to our Sun sounds like it should be humanity's best hope. 4.24 light-years away, closer than anything else in the entire galaxy, sits a star that humanity has dreamed about reaching for decades. Proxima Centauri. The first real destination beyond our solar system. The place where we discovered a rocky planet sitting inside the habitable zone. A world that could theoretically hold liquid water on its surface. It sounds like the beginning of a beautiful story. It is not. In 2025, the ALMA observatory recorded 463 explosive flares from this star in just 50 hours of observation. What the data revealed is a stellar environment so violent, so relentless, and so hostile that the closest star to Earth may also be the most dangerous one near it. If you find this kind of deep science valuable, a like and a subscribe go a long way in helping us keep making it. Now, are you comfortable? Let's begin. Look up tonight. If you are standing anywhere in the southern hemisphere, somewhere below the bright pair of stars known as Alpha Centauri, hiding in the dark like a secret the sky has been keeping for billions of years, there is a point of light so faint that no human eye can see it without a telescope. It is not impressive. It is not beautiful in the way that Sirius is beautiful, or the way Vega burns white and clean against the summer triangle. It does not announce itself. It does not demand your attention. And yet this tiny, invisible ember is the single most important star in the sky for one simple reason. It is the closest star to Earth. Proxima Centauri sits 4.24 light-years from where you are right now. That number rolls off the tongue so easily that it almost sounds manageable. 4.24. It could be a measurement on a ruler. It could be the distance to the next town. But light-years are not miles. A single light-year is roughly 5.88 trillion miles. Multiply that by 4.24 and you arrive at a distance of approximately 25 trillion miles. 25 trillion. If you could somehow board a commercial airliner and fly non-stop at cruising speed toward Proxima Centauri, the flight would take more than 5 million years. You would not arrive. Your species might not arrive. The aircraft itself would have disintegrated into atoms long before the halfway point. And yet, in the language of astronomy, 4.24 light-years is nothing. It is a front porch. It is the gap between your doorstep and the street. The Milky Way stretches roughly 100,000 light-years across. The nearest large galaxy, Andromeda, is 2.5 million light-years away. Against those numbers, Proxima Centauri is so close that it feels almost reachable, almost touchable. Almost like a place that humanity could actually go. That feeling is the beginning of the story. And it is also the beginning of the trap. To understand why Proxima Centauri occupies such a singular place in the human imagination, you need to understand the system it belongs to. Proxima is not a loner drifting through empty space. It is the third and faintest member of a triple star system that includes two much larger and brighter companions, Alpha Centauri A and Alpha Centauri B. Those two stars orbit each other in a gravitationally bound pair, circling their common center of mass once every roughly 80 years. They are both similar to our Sun. Alpha Centauri A is slightly larger, slightly brighter, and slightly hotter. Alpha Centauri B is slightly smaller, slightly cooler, and slightly dimmer. Together, they form a binary that has been studied by astronomers for centuries. To the naked eye, they appear as a single brilliant point of light, the third brightest star visible from Earth, blazing in the constellation Centaurus in the southern sky. Proxima Centauri orbits this pair from an enormous distance. It sits roughly 13,000 astronomical units from the A and B stars. which means it is about 13,000 times farther from them than the Earth is from the Sun. At that distance, it takes Proxima roughly 550,000 years to complete a single orbit around its two brighter companions. It is so far from them that for a long time, after its discovery in 1915 by the Scottish astronomer Robert Innes, scientists were not even certain it was gravitationally bound to the Alpha Centauri system at all. It took until 2017 for high-precision measurements to confirm with strong confidence that Proxima is indeed part of the family, a distant, dim third sibling circling its more luminous relatives in a vast and lonely loop through the dark. But here is the detail that changed everything. Proxima is closer to us than Alpha Centauri A and B are, not by much. The difference is small, roughly 0.1 light-years, a trivial margin by cosmic standards. But it is enough. Proxima Centauri holds the title of the nearest star to our solar system. It has held that title since it was discovered over a century ago, and it will continue to hold it for thousands of years into the future because its slow orbital drift around the Alpha Centauri binary keeps it positioned on our side of the system for an immensely long stretch of time. That title, nearest star, carries a psychological weight that is difficult to overstate. Humans are drawn to what is close. We explore the nearest valley before we cross the mountain range. We map the nearest coastline before we sail the open ocean. When we dream about reaching another star, the first one we look at is the one that is closest. Not the brightest, not the most interesting, the closest. And Proxima Centauri has been sitting in that position for as long as anyone has known it existed, quietly absorbing more human hope and more interstellar ambition than any other star in the galaxy. That hope exploded into something much more tangible on August 24, 2016. On that date, the European Southern Observatory announced a discovery that sent shockwaves through the scientific community and the public alike. A team of astronomers led by Guillaume Anglada Escudé had confirmed the existence of a planet orbiting Proxima Centauri. Not a gas giant, not a frozen ice world far from the star. A rocky planet with a minimum mass close to that of Earth, sitting squarely inside the habitable zone. The habitable zone. Those two words carry an almost mythical charge in astronomy. The habitable zone is the region around a star where temperatures are right for liquid water to exist on a planet's surface. Not too hot for the water to boil away, not too cold for it to freeze solid. Just right. When a planet sits inside that zone, it does not mean life exists there. It does not even mean the planet has water, but it means the conditions are not automatically hostile to the possibility. And for a species that has been searching the sky for any sign that we are not alone, finding a rocky planet in the habitable zone of the nearest star was like finding a door where you expected only a wall. The planet was named Proxima Centauri b. Its orbital period is just 11.2 days. It orbits roughly 20 times closer to its star than Earth orbits the Sun. And yet, because Proxima Centauri is so much dimmer and cooler than our Sun, that close orbit places the planet right in the zone where liquid water could theoretically persist. The discovery was made using the radial velocity method, which detects tiny wobbles in a star's motion caused by the gravitational tug of an orbiting planet. The wobble was faint, barely detectable, the signature of a world pulling on a star with a mass 1/8 that of the Sun, but it was real. It was confirmed through years of painstaking observation using the high-accuracy radial velocity planet searcher instrument at the La Silla Observatory in Chile. The reaction was immediate and intense. Headlines around the world declared that Earth's nearest neighbor might be habitable. Social media erupted. Space agencies issued statements. And almost overnight, a star that most people had never heard of became the most famous stellar address in the galaxy. Not because it was impressive, not because it was beautiful, but because it was close and because it had a planet that carried even the faintest possibility of being like home. And the discoveries did not stop. In 2022, astronomers confirmed a second planet in the system, designated Proxima Centauri d. This world orbits even closer to the star than Proxima b, completing a full orbit in just 5.1 days, at a distance of roughly 0.029 astronomical units. Its mass is estimated at roughly a quarter of Earth's, making it one of the lightest exoplanets ever detected. Proxima d is not in the habitable zone. It orbits far too close for surface conditions to matter to the question of life, but its discovery meant the nearest star did not have one planet. It had a system. Multiple worlds arranged at different distances, each one reinforcing the idea that the closest stellar neighbor was not just a point of light, but a place with structure, a place worth going to. A third planet, designated Proxima Centauri c, had been reported in 2020 as a possible super-Earth, orbiting much farther out, at roughly 1.5 astronomical units, with a period of about 5 years. Its existence has since been disputed, with some researchers suggesting the signal may be an artifact in the data, but even the disputed candidate contributed to the narrative. Every announcement, confirmed or uncertain, added another layer of attention, another reason to point instruments at this one system. The Alpha Centauri neighborhood was becoming the most studied stellar address in the galaxy, and Proxima Centauri sat at the center of it all. Then, in December of 2020, something happened that briefly pushed the Proxima Centauri story from astrophysics into the realm of the extraordinary. The Breakthrough Listen project, the most comprehensive search for extraterrestrial intelligence ever conducted, announced the detection of a narrow-band radio signal that appeared to originate from the direction of Proxima Centauri. The signal, designated BLC-1, was detected by the Parkes radio telescope in Australia. It occupied a single frequency near 980 MHz, a band not typically used by known sources of interference. It did not match any catalogued satellite or terrestrial transmission. It exhibited a frequency drift consistent with a source beyond Earth, and it pointed, within the resolution of the instrument, straight at the nearest star. The announcement was cautious. The Breakthrough Listen team emphasized that the signal was a candidate, not a confirmed detection, but the headlines wrote themselves: a possible alien signal from the nearest star. The excitement was instantaneous and global. For a few weeks, Proxima Centauri was not just the closest star with a habitable zone planet. It was the star that might be talking to us. The signal was eventually identified as human-generated radio interference, most likely from ground-based electronics near the observatory. BLC-1 was not a message from another civilization, it was noise. But the episode revealed something profound about the psychological grip that Proxima Centauri holds on the human imagination. Of all the stars in the sky, of all the billions of candidates where intelligence might have arisen, the one that made the world stop and listen was the nearest one. Not because the signal was particularly strong or unusual, but because it came from there, from the closest star, from the one we had already decided mattered most. The false alarm was a mirror held up to humanity's relationship with proximity. We did not just hope Proxima Centauri had a habitable planet. We hoped someone was already there, waving at us from the front porch. What followed the discovery of Proxima b was a cascade of ambition that revealed just how deeply humans are wired to reach for what feels near. In April of 2016, months before Proxima b was even publicly confirmed, a project called Breakthrough Starshot had already been announced. Backed by $100 million from Russian-Israeli venture capitalist Yuri Milner and supported by a board that included the late Stephen Hawking, breakthrough starshot proposed something that sounded like science fiction. The plan was to accelerate tiny spacecraft, each no larger than a postage stamp, to 20% of the speed of light using a ground-based laser array. At that speed, the craft could reach the Alpha Centauri system in roughly 20 years. 20 years, not 5 million, not 100,000. 20. The target, inevitably, was Proxima Centauri, the nearest star, the one with the rocky planet in the habitable zone. The engineering challenges were staggering. Building a laser powerful enough to accelerate a gram-scale spacecraft to 60,000 kilometers per second would require a facility unlike anything ever constructed. The spacecraft themselves would need to survive the acceleration, navigate across 4 light-years of interstellar space, and then somehow transmit useful data back to Earth using a laser so tiny it could barely be called a device. The project acknowledged that the technology did not yet exist. The timeline was measured in decades. But the ambition was real, funded, and pointed directly at one star. And breakthrough starshot was only the most dramatic example. In the years following the discovery of Proxima b, dozens of research papers explored scenarios for reaching, studying, or even colonizing the Proxima Centauri system. Atmospheric models were built to predict what kind of air the planet might have. Climate simulations were run to estimate whether liquid water could persist on its surface under various conditions. In 2018, a study using general circulation models similar to those used for Earth's climate found that under a wide range of assumptions, Proxima b could sustain enormous areas of liquid water on its surface. The lead researcher, Anthony Del Genio of NASA's Goddard Institute for Space Studies, said the results suggested a decent chance the planet would be habitable. The volume of scientific attention was staggering. By 2023, Proxima Centauri b had become what researchers described as the best-known exoplanet to the general public. It appeared in documentaries, novels, news features, and policy discussions about the future of space exploration. It was the default answer to the question of where humanity might go first beyond the solar system. And that default status was not earned by the planet's characteristics. It was earned entirely by the star's proximity. Proxima b was not the most promising habitable zone planet in the catalogue, it was the closest one. And closeness in the human mind is a form of promise all by itself. The scientific community was careful. Researchers emphasized the uncertainties. They noted that Proxima b's mass was only a minimum estimate because the planet does not transit its star, meaning its orbital inclination is unknown. They acknowledged that the planet's composition, atmosphere, and surface conditions were entirely unconstrained by actual observation. They pointed out that models are only as good as the assumptions they are built on. But the public narrative had already taken shape. Proxima Centauri b was the Earth next door, the closest, potentially habitable world. The first real target for interstellar exploration. And the star it orbited, that dim red ember invisible to the naked eye, had become the most symbolically important star in human history. Not for what it was, but for what it represented. Hope, accessibility, the idea that the universe might have placed a second chance right on our doorstep. This is where the story most people know ends. The nearest star has a planet. The planet might be habitable. We are building plans to go there. The narrative is clean, hopeful, and forward-looking. It fits neatly into the human desire for a frontier, a next step, a place to reach toward when the nights feel too vast and the silence of the cosmos feels too heavy. But there is another story. A story that has been building in the scientific literature for years, growing louder with every new observation, every new data set, every new instrument pointed at this star. And it is a story that takes the hopeful narrative about Proxima Centauri and dismantles it piece by piece, not with speculation, not with pessimism, but with measurement. Because the question that most people never think to ask about the nearest star is not whether it has a planet, it is what kind of star it actually is, what it is doing to its surroundings, what it has been doing for nearly 5 billion years, and whether any world orbiting it could survive what it delivers. Proxima Centauri is not a star like our Sun. It is a fundamentally different kind of object, governed by different internal physics, operating under different rules, producing a different relationship with everything in its vicinity. The Sun is a G-type main sequence star. It is massive enough to maintain a layered internal structure, with a radiative core wrapped in a convective envelope. This architecture produces a relatively stable star with a predictable cycle of activity. The Sun has flares, it has sunspots, it has coronal mass ejections. But these events occur within a framework that is, by stellar standards, orderly. The Sun's activity cycle runs on a roughly 11-year period. Its most violent outbursts, while powerful, are rare and moderated by the structure of its interior. Proxima Centauri has none of this restraint. It is a red dwarf. Specifically, it is classified as spectral type M5.5, placing it at the low-mass end of the M-dwarf category. Its mass is roughly 12.5% that of the Sun. Its diameter is roughly 14% of the Sun's diameter, making it only about 1.5 times the width of Jupiter. If you placed Proxima Centauri next to our Sun, it would look like a glowing coal sitting beside a furnace. Its surface temperature is approximately 3,000 kelvins, compared to the Sun's 5,800. Its total luminosity across all wavelengths is just 0.16% of the Sun's output. In visible light, the kind your eyes can detect, it radiates only 0.0056% as much energy as the Sun. More than 85% of its light is emitted as infrared radiation, invisible to the human eye. This is why you cannot see it from your backyard, despite the fact that it is the closest star in the sky. It is simply too dim, but dim does not mean quiet. And this is where the intuition fails. Because the same property that makes Proxima Centauri so faint is also the property that makes it so dangerous. Its small mass means that its interior operates in a way that is categorically different from the Sun's. Proxima Centauri is fully convective. Unlike the Sun, which has distinct layers where energy moves by different mechanisms, Proxima's interior is a single churning mass. Hot material from the core rises to the surface. Cooler material from the surface sinks back to the core. The entire star participates in this convective cycle, from center to surface, without interruption. This matters enormously for one reason. Convection drives magnetic field generation. And in a fully convective star, the magnetic field is not confined to specific layers or regions the way it is in the Sun. It is generated throughout the entire volume of the star. The result is a magnetic field that is disproportionately powerful for a star of this size. Proxima Centauri's magnetic field strength has been measured at roughly 450 to 750 Gauss. For context, the Sun's average surface magnetic field is only about 1 Gauss, though it can be much higher in localized regions like sunspots. Proxima's field is stronger, more pervasive, and more turbulent than the Sun's global field. Despite the star being a fraction of the Sun's size, that magnetic field is the engine behind everything that makes Proxima Centauri dangerous. When magnetic field lines on the surface of any star become twisted, compressed, and tangled, they store energy. Eventually, the configuration becomes unstable. The field lines reconnect, snapping into new configurations and releasing the stored energy in a violent burst. This is what produces a stellar flare. On the Sun, this process is significant but comparatively restrained. On Proxima Centauri, it is relentless. The star has been classified as a flare star for decades. It is one of the most magnetically active stars in the solar neighborhood. And here is the fact that should trouble anyone who has attached hope to this system. Proxima Centauri is approximately 4.85 billion years old. It is roughly the same age as our Sun. For most types of stars, magnetic activity decreases over time as the star's rotation slows and its internal dynamo weakens. The Sun was more active in its youth than it is today. Over billions of years, it calmed down. This calming is part of what made life on Earth possible. The Sun's temper cooled as the planet matured. Proxima Centauri did not follow this path. Its rotation period is approximately 83 days, which is slow. Slow rotation in a Sun-like star would mean low magnetic activity. But Proxima is not Sun-like. Its fully convective interior sustains powerful magnetic fields regardless of rotation speed. The dynamo mechanism in fully convective stars does not depend on the same rotation-convection coupling that governs solar-type stars. It can maintain fierce activity even at advanced ages, even with slow rotation. The result is a star that is nearly 5 billion years old and still behaves magnetically and energetically. Like an adolescent having a tantrum, approximately 88% of Proxima Centauri's surface may be magnetically active at any given time. Compare that to the Sun, where even at the peak of its 11-year cycle, the active regions cover a relatively small fraction of the surface. Proxima's corona maintains a temperature of roughly 3.5 million kelvins, even during quiet periods, significantly hotter than the Sun's 2 million Kelvin corona. And its quiescent X-ray luminosity, the baseline radiation output between flares, is comparable to the Sun's total X-ray output, despite Proxima being a fraction of the Sun's size. Pound for pound, Proxima Centauri is pumping out X-rays at a vastly higher rate than our star. Now consider what this means for a planet orbiting inside the habitable zone. Proxima Centauri b orbits at 0.0485 astronomical units from its star. That is less than 1/20th the distance between Earth and the Sun. It is closer to Proxima than Mercury is to our Sun. The only reason this orbit qualifies as habitable is that Proxima is so dim that the amount of visible light and heat reaching the planet at that distance is comparable to what Earth receives from the Sun. The temperature math works out, barely, but visible light and heat are not the only things a star delivers to its planets. There is also ultraviolet radiation. There are X-rays. There is the stellar wind, a continuous stream of charged particles flowing outward from the star. And there are flares, sudden explosive releases of energy that can multiply the star's output across the electromagnetic spectrum by orders of magnitude in seconds. At Proxima b's orbital distance, the planet receives roughly 30 times more extreme ultraviolet radiation than Earth receives from the Sun. It receives approximately 250 times more X-rays. The stellar wind pressure hitting the planet is estimated to be roughly 10,000 times greater than what the solar wind exerts on Earth. 10,000 times. That is not a moderate increase. That is not a difference you engineer around. That is a fundamentally different relationship between a star and its planet. And the habitable zone, the region that made Proxima b so exciting in the first place, is the very reason this radiation is so intense. Because the zone is so close to the star, the planet cannot escape the consequences of its host's behavior. On Earth, we sit far enough from the Sun that even its most violent outbursts are weakened by distance before they reach us. We have 93 million miles of vacuum acting as a buffer. Proxima b has less than 5 million miles. There is almost nowhere for the energy to dissipate before it arrives. There is one more structural detail about this system that compounds everything described above, and it involves gravity itself. At Proxima B's orbital distance, tidal forces from the star are strong enough to have almost certainly locked the planet's rotation to its orbit. One hemisphere permanently faces the star. The other faces away into eternal darkness. There is no sunrise. There is no sunset. The planet does not spin the way Earth does. And that missing spin has consequences that reach far deeper than the difference between a permanent day side and a permanent night side. It affects the planet's ability to protect itself. On Earth, our rapid rotation helps generate the magnetic field that shields the atmosphere from the solar wind. A planet that barely rotates may not be able to generate that shield at all. Around a star like Proxima Centauri, that vulnerability could be fatal. The details of how tidal locking undermines a planet's defenses, and why the stellar wind and radiation at this distance make that vulnerability so devastating, are part of the mechanical story of how Proxima Centauri's interior architecture creates an environment that is hostile by design. That story requires understanding the star from the inside out, not just its surface behavior, but the deep structural reasons why it cannot stop being dangerous. Because the flares, the radiation, the wind, the locking, the atmospheric erosion, these are not separate problems. They are connected consequences of a single underlying cause. What happens when a star is built without the internal boundaries that keep our sun restrained? The machine that drives all of it is the star itself. And understanding that machine is where the real picture of Proxima Centauri begins to take shape, and we have not yet discussed the flares themselves, what Proxima Centauri does when its magnetic field snaps. What happens in the seconds and minutes after a reconnection event tears through its corona. What that means for anything orbiting within 5 million miles. Because the flares are not a footnote in this story. They are the centerpiece. And the data collected over the last several years has revealed a level of violence that transforms Proxima Centauri from a merely hostile star into something that resembles a weapon pointed at its own planets. That data is where we go. Next, to understand why Proxima Centauri is dangerous, you cannot simply list its properties and compare them to the Sun's. You have to understand the machine. You have to see how the star works from the inside out, how the architecture of its interior produces behavior that no sun-like star can replicate, and why that architecture creates a relationship with nearby planets that is not merely harsh, but structurally incompatible with the conditions life requires. The danger is not an accident. It is engineered into the physics of what this star is. Start at the center. Every star is a battle between two forces. Gravity pulls inward, trying to crush the star into a point. Nuclear fusion pushes outward, generating energy that creates pressure to resist the collapse. The star exists in a state of equilibrium between these two forces, a balance maintained for as long as the fuel lasts. In our Sun, hydrogen atoms in the core are fused into helium at temperatures exceeding 15 million kelvins. The energy released by this fusion radiates outward, passing first through a vast region called the radiative zone, where photons bounce from particle to particle in a slow, random walk that can take hundreds of thousands of years to traverse. Above the radiative zone sits the convective zone, where the energy transport mechanism changes. Here, hot plasma rises to the surface, releases its energy, cools, and sinks back down. This layered structure, radiative interior wrapped in a convective envelope, is the defining feature of solar-type stars, and it is precisely this structure that Proxima Centauri does not have. Proxima Centauri's mass is so low that the physics of energy transport inside it never transitions from convection to radiation. The entire star, from its core to its surface, operates as a single convective system. hot material rises from the nuclear burning center. It travels all the way to the photosphere. It releases energy. It cools. It sinks back to the center. There is no radiative zone acting as a buffer. There is no separation between the deep interior and the outer layers. The star is one continuous engine of churning plasma, a pot of liquid fire that stirs itself from bottom to top without interruption. This might sound like a minor structural difference. It is not. It changes everything about how the star behaves, how long it lives, how it manages its fuel, and, most critically, how it generates the magnetic fields that determine what happens to anything in its vicinity. In the Sun, the boundary between the radiative zone and the convective zone, a region called the tachocline, plays a central role in magnetic field generation. The difference in rotation rates between these two layers creates shearing forces that stretch, twist, and amplify magnetic field lines. This is the solar dynamo. It produces the 11-year cycle of sunspot activity. It governs when and where flares occur. And because it is tied to a specific structural boundary, it produces magnetic behavior that is cyclic, somewhat predictable, and confined to specific regions of the solar surface. Proxima Centauri has no tachocline. It has no boundary between layers. There is no shearing interface to organize the magnetic field generation into a neat cycle. Instead, the dynamo operates throughout the entire convective volume of the star, driven by turbulent motions that are chaotic, distributed, and difficult to predict. The magnetic field that results is not organized into tidy bipolar regions the way sunspots are on the Sun. It is tangled, pervasive, and erupts from across the entire surface simultaneously. Researchers have estimated that at any given moment, the vast majority of Proxima's surface is magnetically active. On the Sun, even at solar maximum, active regions cover a comparatively modest fraction of the photosphere. On Proxima, the surface is essentially one continuous active region. This is why the star does not calm down with age the way the Sun does. The solar dynamo depends on rotation. As the Sun ages, it loses angular momentum through its stellar wind and gradually spins down. Slower rotation means weaker shearing at the tachocline, which means a weaker dynamo, which means fewer and less intense flares. This is a well-established relationship in stellar physics, and it is the reason the Sun today is far gentler than the Sun of 4 billion years ago. Earth's early history was shaped by a more violent star. The fact that the Sun mellowed over time is part of why complex life eventually became possible here. Proxima Centauri's dynamo does not follow this rule. Because it operates through distributed turbulent convection rather than through rotational shearing at a structural boundary, it remains effective even at slow rotation speeds. Proxima's rotation period is approximately 83 days. That is slow. For a solar-type star, a rotation period that long would correspond to extremely low magnetic activity, a star in deep magnetic retirement. But Proxima is not solar-type. Its fully convective dynamo continues to generate powerful magnetic fields despite the slow rotation, sustaining a level of surface activity that would be impossible for a Sun-like star of the same age. The consequence is a star that has been magnetically violent for nearly 5 billion years and shows no signs of stopping. The activity may be lower than it was in the star's youth, but it has not dropped to the quiet baseline that Sun-like stars achieve over the same time frame. Proxima Centauri will remain active for an almost incomprehensible span of time. Red dwarfs of this mass consume their hydrogen fuel so slowly, and their fully convective interiors mix that fuel so thoroughly that they can sustain nuclear fusion for trillions of years. Not billions. Trillions. Our Sun will exhaust its hydrogen in roughly another 5 billion years, swell into a red giant, and eventually shed its outer layers to become a white dwarf. Proxima Centauri will still be burning when the Sun is a cold, dark cinder, it will still be flaring. It will still be bathing its surroundings in radiation and charged particles long after our entire solar system has ceased to exist as a recognizable structure. The reason for this extraordinary longevity is mechanical, and it connects directly to the full convection that makes the star so dangerous. In a sun-like star, only the core participates in nuclear fusion. The hydrogen in the outer layers, the vast majority of the star's mass, never reaches the temperatures and pressures needed to fuse. It sits there, unused, for the star's entire life. When the core exhausts its hydrogen supply, the star has burned through only roughly 10% of its total fuel. The rest remains locked in the envelope, inaccessible. This is why sun-like stars leave the main sequence after roughly 10 billion years. They do not run out of hydrogen. They run out of hydrogen in the one place where hydrogen can burn. Proxima Centauri's fully convective interior eliminates this inefficiency entirely. Because material circulates continuously from the core to the surface and back, fresh hydrogen is constantly delivered to the fusion region, while processed helium is carried away and redistributed. The star does not burn through a fixed core supply and then die. It cycles nearly all of its hydrogen through the furnace over trillions of years, extracting almost every available unit of energy from its fuel before finally exhausting it. And when it does finally exhaust that fuel, it will not swell into a red giant the way the sun will. The red giant phase occurs because a sun-like star develops a dense core of helium ash that contracts and heats, while a hydrogen-burning shell around it drives the outer layers outward in a dramatic expansion. Proxima's fully mixed interior never develops that layered ash structure. There is no inert helium core. There is no shell burning. When its hydrogen is finally spent, the star will simply dim, gradually, quietly. It will contract into a helium-white dwarf without ever expanding, without ever brightening, without ever going through the dramatic death sequence that sun-like stars experience. It will fade from a dim red ember to a cold, dark cinder over a timescale so vast that the current age of the universe is a small fraction of it. This matters for the habitability story because it closes the last theoretical escape hatch a thoughtful person might reach for. Around some stars, there are windows of opportunity, periods where the star is calmer, phases where conditions temporarily shift. The sun's gradual mellowing over billions of years created exactly such a window, and life on Earth exploited it. Around Proxima Centauri, no such window exists. The star will not calm down with age the way the sun did. It will not enter a red giant phase that temporarily pushes the habitable zone outward to safer distances where a planet might catch a reprieve. It will not undergo any structural transition that alters its relationship with nearby planets. It will simply continue doing exactly what it is doing now, flaring, radiating, eroding, for longer than the current age of the universe multiplied by 100. The punishment is not just severe. It is, for all practical purposes, eternal. For a planet, this means there is no waiting it out. There is no grace period where the star settles into a calm old age and conditions improve. Around Proxima Centauri, that window never opens. The star's hostility is not a phase. It is a permanent condition, sustained by an internal architecture that does not permit the kind of magnetic retirement that made Earth's history possible. Now, consider the habitable zone. Around the Sun, the habitable zone sits at a comfortable distance. Earth orbits at 1 astronomical unit, roughly 93 million miles from the solar surface. At that distance, the Sun's radiation is strong enough to warm the planet, but weak enough that a modest atmosphere and a magnetic field can manage the high-energy components. The stellar wind at Earth's distance is a gentle breeze compared to what it is near the solar surface. Flares, even powerful ones, are attenuated by the vast gulf of space between the Sun and the Earth. Distance is a shield. Around Proxima Centauri, the habitable zone is not distant. It cannot be distant. The star is so dim that a planet must orbit extremely close to receive enough energy to maintain liquid water on its surface. The habitable zone sits at roughly 0.05 astronomical units, a distance so small that it is difficult to convey without analogy. Imagine shrinking Earth's orbit until the Sun appeared not as a small bright disk in the sky, but as a massive glowing wall consuming a significant portion of the horizon. That is approximately the visual relationship between Proxima Centauri and anything orbiting in its habitable zone. The star is right there, not a distant furnace but an immediate, overwhelming presence, and everything it does is delivered at point-blank range. This proximity creates a cascade of problems that compound one another in ways that do not occur around Sun-like stars. The first, and most fundamental, is tidal locking. When a planet orbits this close to its host star, gravitational tidal forces act on the planet's structure, creating bulges in the rocky body that dissipate rotational energy as heat. Over time, this tidal friction slows the planet's rotation until it matches the orbital period. The planet becomes locked, with one face permanently turned toward the star and the other permanently turned away. For Proxima b, with its 11.2-day orbit, tidal locking is considered nearly inevitable unless the planet has an unusually high orbital eccentricity that could trap it in a higher-order spin-orbit resonance, similar to Mercury's 3:2 resonance with the Sun. The implications of tidal locking extend far beyond the obvious difference between a permanent day side and a permanent night side. A locked planet rotates extremely slowly relative to its own axis. On Earth, the rapid rotation, one full turn every 24 hours, drives powerful convective motions in the liquid iron outer core. These motions generate Earth's magnetic field through a process called the geodynamo. The magnetic field extends far into space, creating a protective magnetosphere that deflects the solar wind and shields the atmosphere from erosion by charged particles. Without the geodynamo, Earth would have lost its atmosphere to the solar wind billions of years ago, the same fate that befell Mars when its internal dynamo shut down. A tidally locked planet rotates once every 11 days. That is roughly 11 times slower than Earth. Slower rotation means weaker Coriolis forces in the core, which means less efficient convective dynamo action, which means a weaker magnetic field. Some models suggest a tidally locked planet could still generate a magnetic field if other conditions are favorable, such as vigorous core convection driven by internal radioactive heating. But the field would almost certainly be weaker than Earth's, and around Proxima Centauri, a weak magnetic field is not a minor vulnerability. It is potentially fatal to any atmosphere the planet might possess. The reason involves the stellar wind. Our Sun produces a continuous outflow of charged particles, mostly protons and electrons, streaming outward at speeds of roughly 400 to 800 kilometers per second. At Earth's distance, the density and pressure of this wind are modest. Earth's magnetosphere deflects most of it, channeling particles toward the poles where they produce auroras. The system works because the wind is weak enough and the field is strong enough that the balance holds. Around Proxima Centauri, the wind is not weak. The planet orbits so close that the stellar wind density is estimated to be 10 to 1,000 times greater than what Earth experiences, depending on the phase of Proxima's roughly 7-year magnetic activity cycle. The dynamic pressure of this wind is crushing by solar standards. Models of the space environment around Proxima b have shown that the wind pressure can compress a planetary magnetosphere to a fraction of the size Earth's magnetosphere achieves. If the planet's magnetic field is weak, as tidal locking suggests it would be, the magnetosphere could be pushed so close to the surface that the upper atmosphere sits outside the protected zone. At that point, the stellar wind makes direct contact with atmospheric gas. Charged particles collide with atmospheric molecules, transferring enough energy to knock them free of the planet's gravity. Molecule by molecule, atom by atom, the atmosphere bleeds into space. This process is called atmospheric sputtering, and it is not fast by human standards. It operates over hundreds of millions to billions of years. But Proxima Centauri has been delivering this punishment for nearly 5 billion years, and the stellar wind is not the only erosion mechanism at work. There is also photoevaporation. Extreme ultraviolet radiation from the star heats the upper atmosphere of the planet to temperatures where the gas expands outward, puffing up above the magnetospheric boundary and becoming vulnerable to the wind. This is sometimes called hydrodynamic escape, and it is especially effective at removing lighter molecules like hydrogen. When water vapor in an atmosphere is broken apart by ultraviolet radiation into hydrogen and oxygen, the hydrogen escapes first because it is the lightest element. The oxygen left behind can either escape more slowly or combine with surface minerals through oxidation. Either way, the water is gone, not relocated, not frozen, destroyed at the molecular level and dispersed into the void. The radiation that drives this process is not occasional, it is constant. Proxima Centauri's baseline extreme ultraviolet and X-ray output, even between flares, is intense enough to drive significant atmospheric erosion over geological time. Researchers studying the star's spectral energy distribution have found that the integrated dose of high-energy radiation received by Proxima b over its lifetime is between 7 and 16 times higher than the total dose Earth has received from the Sun over the same period. And that comparison uses the Sun's current output, which is itself lower than the Sun's output during its more active youth. The actual disparity may be even larger. But the baseline radiation is only part of the problem. What makes Proxima Centauri's environment genuinely different from the solar neighborhood is what happens during the star's pre-main sequence phase. And this is a detail that changes the entire habitability picture in a way that many popular accounts of Proxima b never mention. All stars go through a period of contraction before they reach the stable hydrogen burning phase called the main sequence. During this pre-main sequence phase, the star is larger, brighter, and hotter than it will be during its mature life. For the Sun, this phase was relatively brief, lasting roughly 50 million years. The Sun contracted quickly, reached the main sequence, and settled into stable hydrogen fusion. For red dwarfs, the story is completely different. Low-mass stars contract much more slowly because they have less gravitational energy driving the collapse. Proxima Centauri took an estimated 100 to several hundred million years to contract to its final main sequence size. During that entire period, it was significantly more luminous than it is today. Its habitable zone was farther from the star than it is now. The orbit that Proxima b currently occupies was not inside the habitable zone during the pre-main sequence. It was too close. It was inside the zone where a runaway greenhouse effect would have occurred. A runaway greenhouse is exactly what it sounds like. The planet's surface becomes hot enough that any water present evaporates into the atmosphere. Water vapor is a powerful greenhouse gas. More water vapor means more heat trapped, which means more evaporation, which means more heat trapped. The cycle feeds itself until all surface water has been converted to atmospheric steam. At that point, the upper atmosphere is saturated with water vapor, which ultraviolet radiation from the star splits into hydrogen and oxygen. The hydrogen escapes to space. the water is permanently lost. For Proxima b, models suggest this runaway phase could have lasted up to 180 million years. 180 million years of continuous water loss before the star dimmed enough for the habitable zone to migrate inward to where the planet actually orbits. By the time conditions theoretically became suitable for liquid water, there may have been no water left to condense. This is the pre-main sequence water loss problem, and it is specific to planets around red dwarfs. Around Sun-like stars, the pre-main sequence phase is too short to completely desiccate a planet, especially one that formed with a significant water inventory. Around red dwarfs, the phase lasts long enough to strip a planet of its entire ocean. Some researchers have proposed scenarios in which a thick hydrogen envelope could shield a terrestrial planet during the pre-main sequence, insulating the water reservoir beneath it until the star settles down. But this requires a specific set of initial conditions that may or may not apply to Proxima b, and we have no observational data to constrain which scenario actually occurred. What we do have are models, many of them, and the models do not converge on a single answer. Some show a habitable Proxima b with oceans and moderate temperatures. Others show a desiccated husk with a thick oxygen atmosphere left over from the decomposition of water, oxygen that accumulated not because of photosynthesis, but because the hydrogen was stripped away. Still others show a planet with no atmosphere at all, scoured clean by billions of years of stellar wind erosion. The honest, scientific answer, as of the most current research, is that we do not know which of these outcomes is real. The atmospheric state of Proxima b is unconstrained by observation. The planet does not transit its star, which means we cannot use transmission spectroscopy to analyze its atmosphere the way we can with transiting exoplanets. Direct imaging of the atmosphere is beyond the reach of current instruments, though future telescopes like the extremely large telescope under construction in Chile may eventually be able to characterize it. A March 2025 study found that with the European Extremely Large Telescope, it might be possible to rule out a sub-Neptune atmosphere in as little as a single hour of observation, and certain biosignature pairs might be detectable in roughly 10 hours under optimistic assumptions. But until those observations are made, the question of whether Proxima b has an atmosphere remains open. What is not open is the question of whether the environment is hostile. On that point, the physics is clear. The combination of extreme proximity to a magnetically active star, intense and sustained ultraviolet and X-ray irradiation, a stellar wind with crushing dynamic pressure, the near certainty of tidal locking, the likely weakness of any planetary magnetic field, and the extended pre-main sequence period, during which water could have been permanently lost, creates a system that is hostile by design, not hostile by accident. Hostile because the fundamental physics of a low-mass, fully convective star requires its habitable zone to be located in a region where the word habitable becomes a bitter irony. And there is one more layer to this structural problem that deserves attention before we move to the flares themselves, because it involves a threat that the Sun never poses to Earth, but that Proxima Centauri delivers as a matter of routine. Coronal mass ejections. On the Sun, a coronal mass ejection is an enormous eruption of magnetized plasma, billions of tons of charged material hurled outward from the corona at speeds that can exceed 1,000 kilometers per second. CMEs are often associated with solar flares, but are physically distinct events. A flare is a burst of electromagnetic radiation. A CME is a physical expulsion of matter. When a CME strikes Earth's magnetosphere, it can compress the magnetic field, trigger geomagnetic storms, disrupt satellites, and in extreme cases, affect power grids on the surface. The Carrington event of 1859, the most powerful geomagnetic storm in recorded history, was caused by a CME that struck Earth's magnetosphere and induced electrical currents strong enough to set telegraph equipment on fire. Earth survives these events because of two factors: distance and magnetic shielding. The Sun's CMEs spread out as they travel outward, reducing their density and impact by the time they reach 1 astronomical unit. And Earth's magnetic field remains strong enough to prevent direct atmospheric erosion in all but the most extreme theoretical scenarios. Around Proxima Centauri, neither of these protections applies. The planet is so close that a CME has almost no distance over which to dissipate. The material arrives concentrated, dense, and fast. And the planetary magnetic field, weakened by tidal locking, may not be strong enough to prevent the CME from making direct contact with the upper atmosphere. In 2020, researchers using the Australian Square Kilometre Array Pathfinder detected radio emissions from Proxima Centauri that bore the hallmarks of a solar-type coronal mass ejection. The signal, a Type 4 radio burst, was simultaneously observed alongside an optical flare, and the probability that the two events were unrelated was calculated at less than 1 in 128,000. While this is not a definitive detection of a CME from a red dwarf, it is the most compelling evidence to date that Proxima Centauri produces these eruptions. And if it does, the consequences for any orbiting planet are severe. A CME impacting a weakly magnetized planet at close range does not just compress the magnetosphere, it can peel it open. The magnetic reconnection between the CME's embedded magnetic field and the planet's field can create temporary holes in the magnetosphere through which charged particles pour directly into the upper atmosphere. The erosion during a single major CME event can exceed the erosion caused by weeks or months of steady stellar wind bombardment. And if Proxima Centauri produces CMEs at a rate proportional to its flare rate, the planet could be experiencing these atmospheric assaults regularly, possibly multiple times per year. The Australian astronomer Andrew Zick, whose team reported the radio burst detection, summarized the implications directly. He said, "It seems likely that the galaxy's most common stars, red dwarfs, would not be great places to find life as we know it." That assessment was not pessimism, it was a measurement translated into plain language. This is the picture of Proxima Centauri as a physical system, and it is the picture that most popular narratives about the nearest star either gloss over or ignore entirely. The star is not just dim and close. It is a magnetically hyperactive engine that has been punishing its surroundings for nearly 5 billion years without pause, whose habitable zone is located in a region that guarantees exposure to extreme radiation and stellar wind, whose planets are almost certainly tidally locked in a configuration that undermines their ability to protect themselves, and whose pre-main sequence evolution may have already destroyed any water the nearest planet ever had before the star even reached adulthood. And all of this describes the baseline, the normal operating conditions, the quiet state of the system when nothing unusual is happening. What happens when the magnetic field lines snap, when the corona tears itself apart, when the star erupts with a flare so powerful that it briefly becomes 14,000 times brighter in ultraviolet light and releases more energy in seconds than the sun delivers in an entire day? That is another story entirely. And the instruments have been watching. The data is in. 463 flares in 50 hours. A star that does not simply have flares. A star that is, in a very real sense, a flare machine. That story comes next. The first warning came not from a space telescope or a radio array in a desert, but from a relatively modest, robotic instrument perched on a mountaintop in Chile. The Evryscope, a hemispheric sky survey instrument operated by the University of North Carolina at Chapel Hill, was designed to monitor the entire visible sky simultaneously, recording the brightness of millions of stars every 2 minutes throughout the night. It was a wide net, not a sharp spear, built to catch rare events, by watching everything at once. In March of 2016, it caught something from Proxima Centauri that no one had seen before. The star brightened, not by a small amount. Proxima Centauri's flux increased by a factor of 68 in visible light for a brief window. A star that is normally invisible to the naked eye, despite being the closest star in the sky, became bright enough that a human being standing in the southern hemisphere and looking in exactly the right direction could theoretically have seen it without any instrument at all. A naked-eye superflare from a star 4.24 light-years away. The bolometric energy of the event was estimated at roughly 10 to the 33.5 ergs, placing it firmly in superflare territory and making it the most powerful flare ever recorded from Proxima Centauri at that time. The Evryscope team, led by Ward Howard, did more than document a single event. They had been monitoring Proxima Centauri continuously and had recorded 23 other large flares over the preceding 2 years, with bolometric energies ranging from 10 to the 30.6 ergs to 10 to the 32.4 ergs. Using the rate of those events, combined with the detection of the single superflare, they estimated that Proxima Centauri produces at least 5 superflares per year. 5 events annually, each one releasing energy comparable to or exceeding the most powerful eruptions ever observed from our Sun, delivered to a planetary system whose habitable zone sits less than 5 million miles from the source. The team went further. They modeled the photochemical consequences of this flare rate on a hypothetical Earth-like atmosphere at Proxima B's orbital distance. Specifically, they examined what happens when high-energy particles from repeated superflares generate nitrogen oxide compounds in the upper atmosphere. The results were stark. The repeated flaring was sufficient to reduce the ozone content of such an atmosphere by 90% within 5 years. Complete ozone depletion could occur within several 100,000 years. Their paper noted that the resulting surface ultraviolet radiation levels would exceed the tolerance of some of the hardiest known organisms. The Evryscope had not just detected a spectacular flare, it had quantified a pattern of destruction fast enough and relentless enough to strip a planet of its chemical defenses in what amounts to a geological instant. That was 2016. The same year Proxima b was announced. The same year the world celebrated the discovery of a rocky planet in the habitable zone of the nearest star. The Evryscope results were published and discussed in the scientific community. And then the excitement about the planet continued, almost uninterrupted, because the human capacity to hold 2 contradictory narratives, one of hope and one of warning, is nearly unlimited when the stakes feel large enough. 3 years later, the warning grew louder. On May 1st, 2019, 9 telescopes were pointed at Proxima Centauri simultaneously. This was not a coincidence. It was a coordinated campaign, the most ambitious multi-wavelength observation of the nearest star ever attempted. The team, led by Meredith McGregor at the University of Colorado at Boulder, had arranged coverage across the electromagnetic spectrum, from radio waves to ultraviolet light. Using both ground-based and space-based instruments, the goal was straightforward: watch the star, record whatever it does, and, for the first time, capture its behavior across multiple wavelengths at the same moment, so that when something happened, the picture would be complete. Something happened. At a moment that 5 of the 9 telescopes were actively recording, Proxima Centauri erupted. The star suddenly became 14,000 times brighter in far ultraviolet light. The increase took seconds, not minutes, not hours, seconds. In the time it takes to draw a single breath, the nearest star to Earth transformed from an object too faint to see with the naked eye into an ultraviolet beacon of extraordinary intensity. The energy released was estimated to be roughly 100 times more powerful than any comparable flare ever observed from our Sun. That sentence needs to be listened carefully because the comparison is deceptive in its simplicity. Solar flares are not gentle events. The most powerful solar flares, classified as X-class events, release energies on the order of 10 to the 32 ergs across the electromagnetic spectrum. They can disrupt radio communications, damage satellite electronics, and in extreme cases, threaten power grid infrastructure on the ground. The Carrington event was triggered by a flare and an associated coronal mass ejection that induced electrical currents across telegraph networks worldwide. These are serious events. And the flare that Proxima Centauri produced on May 1, 2019, dwarfed them. The bolometric energy of the event placed it firmly in the category that astronomers call a superflare. Events with total energy outputs exceeding 10 to the 33 ergs. The 2019 event surpassed even the Evryscope superflare of 3 years earlier. It was one of the most powerful flares ever observed from any star in the entire Milky Way at the time of its detection. What made the observation scientifically transformative was not just the power of the flare, but the multi-wavelength coverage. For the first time, astronomers could see what was happening across the entire electromagnetic spectrum during a major Proxima Centauri eruption, and what they found added a disturbing new dimension to the picture. The millimeter wavelength emission and the ultraviolet emission were tightly correlated. They rose and fell together in near-perfect synchronization. This was significant because millimeter wavelength radiation from stellar flares is produced by a specific physical mechanism: energetic electrons spiraling through magnetic fields, a process called gyrosynchrotron emission. These are not photons generated by thermal heating. They are signatures of particles being accelerated to enormous speeds, close to the speed of light, by the magnetic reconnection event that drives the flare. The tight correlation meant that the particle acceleration and the radiation burst were coupled more directly than many models had predicted. The flare was not just a flash of light, it was a particle cannon, simultaneously blasting the surrounding space with electromagnetic radiation and high-energy charged particles in a coordinated assault that a planet at close range would have no practical way to deflect. McGregor and her team published their findings in the Astrophysical Journal Letters in 2021. The paper drew immediate attention to a question that had been simmering in the background of the Proxima b habitability debate for years. If the star produces events like this, what are they doing to the planet? But here is the part of the story that the 2019 observation only hinted at. That superflare was spectacular, it was dramatic, it made headlines, and it was not an isolated incident. It was a single data point drawn from a population of events so numerous, so relentless, and so persistent that the word flare begins to feel inadequate. Proxima Centauri does not have flares the way the Sun has flares. The Sun produces flares occasionally, with major events occurring a few times per solar cycle and truly powerful ones arriving once every few years or decades. Proxima Centauri produces flares the way a machine produces output, continuously, automatically, without pause. The first large-scale quantification of this behavior came from the Transiting Exoplanet Survey satellite, known as TEAS. In 2019, researchers analyzed roughly 50 days of continuous TESS photometry of Proxima Centauri and identified 72 distinct flare events, 72 flares in 50 days. That is a rate of approximately 1.5 flares per day. 7.2% of the total observation time was classified as active flaring. The energies ranged from 10 to the 30 ergs to 10 to the 32 ergs in the TESS optical passband, with bolometric energies roughly 5 times higher. The study further estimated that superflares should occur approximately 3 times per year. Events 10 times more energetic, on the order of 10 to the 34 ergs, could be expected roughly once every 2 years, 3 superflares per year, every year, for billions of years. To put that in perspective, the Sun produces a superflare-class event perhaps once every several thousand years. The difference in superflare frequency between Proxima Centauri and the Sun is not a factor of 2 or 5, it is a factor of thousands. The two stars occupy entirely different regimes of magnetic behavior, but even the test data turned out to be an undercount. The reason involves a limitation of optical observations. TESS observes, in visible and near-infrared wavelengths, the part of the spectrum where stellar flares produce their most dramatic brightness increases. But flares are not monochromatic events. They emit energy across the entire electromagnetic spectrum, and the distribution of that energy across wavelengths is not uniform. Some flares that are modest at optical wavelengths can be powerful at millimeter wavelengths. If you only watch in one part of the spectrum, you miss events happening in another. This is what the ALMA observatory revealed. And the numbers changed everything. In March of 2025, a team led by Kiana Burton of the University of Colorado and Meredith McGregor, now at Johns Hopkins University, published the results of the most comprehensive millimeter wavelength study of Proxima Centauri ever conducted. Using approximately 50 hours of observations from the Atacama Large Millimeter Sub-Millimeter Array, the team detected 463 flare events. 463. In 50 hours. That is approximately 9 flares per hour, 1 flare roughly every 6.5 minutes, sustained across the entire observation period. The energies ranged from 10 to the 24 ergs to 10 to the 27 ergs in the ALMA bandpass, with the most powerful event reaching a flux density of 119 millijanskis, an increase of roughly 1,000 times the star's quiescent millimeter emission in a burst lasting approximately 16 seconds. Most of the flares were far briefer, with durations ranging from 3 to 16 seconds, a 3-second flare. A burst of accelerated particles and radiation that lasts about as long as it takes to say the words Proxima Centauri out loud. The team constructed the first cumulative flare frequency distribution at millimeter wavelengths for any Dwarf star. What Burton and McGregor found was that the power law index for Proxima Centauri's millimeter flares was significantly steeper than the power law observed at optical wavelengths. In plain language, the millimeter flaring is much more frequent than the optical flaring. If you only observe in visible light, you are seeing the tip of the iceberg. The bulk of the flare activity is happening at wavelengths that optical telescopes cannot detect. McGregor stated the finding directly. She said, the millimeter flaring seems to be much more frequent and follows a different power law than what is observed at optical wavelengths. She emphasized that if researchers only look at optical wavelengths, they are missing critical information. ALMA, she noted, is the only millimeter interferometer sensitive enough to make these measurements. The implication is stark. Every previous estimate of Proxima Centauri's flare rate based on optical data alone was an underestimate. The star is more active than we thought. The particle environment around it is more intense than we calculated. And the energy being delivered to Proxima B's orbital distance is higher than models based on optical observations predicted. The progression of discovery tells its own story. In 2016, the Evryscope caught a single superflare and estimated that 5 such events occur per year. In 2019, TESS provided the first continuous optical monitoring and found 72 flares in 50 days. In the same year, The multi-wavelength campaign captured a monster eruption and revealed the tight coupling between radiation and particle acceleration. And in 2025, ALMA pulled back the curtain on an entire hidden layer of activity, showing that the star flares 9 times per hour in a wavelength regime that previous studies had barely explored. Each step revealed more activity, not less. The trend line points in one direction only. The star is worse than we thought, and each time we look more closely, it gets worse again. Now, consider what 463 flares in 50 hours means for a planet orbiting at 0.0485 astronomical units. Each flare, no matter how brief, releases a burst of electromagnetic radiation across the spectrum. Extreme ultraviolet photons arrive at the planet at the speed of light, reaching it in approximately 24 seconds after leaving the stellar surface. These photons deposit energy in the planet's upper atmosphere, heating it, ionizing atmospheric molecules, and driving hydrodynamic escape. Each flare also accelerates charged particles, electrons and protons, to significant fractions of the speed of light. These stellar, energetic particles travel outward from the star, and depending on the magnetic field geometry, can reach the planet within minutes to hours. When they arrive, they collide with atmospheric molecules with enough energy to knock atoms free, contribute to sputtering, and generate secondary radiation through interactions with atmospheric gas. To understand what this bombardment actually looks like at the planet's distance, researchers have turned to 3-dimensional magneto-hydrodynamic simulations of the space environment around Proxima b. These models take the observed magnetic field geometry of Proxima Centauri, derived from Zeeman Doppler imaging, and use it to compute the structure of the stellar wind, the shape of the interplanetary magnetic field, and the conditions at the planet's orbital distance. The results are vivid and grim. During quiet periods, the stellar wind dynamic pressure at Proxima b's location already exceeds the solar wind pressure at Earth by factors of hundreds to thousands. The planet orbits so close that during certain phases of the star's magnetic cycle, it sits inside the Alphane surface, the boundary within which the stellar wind has not yet fully accelerated, and the magnetic field of the star still dominates the local environment. Being inside the Alphane surface means the planet is effectively embedded in the star's extended corona, connected to the stellar magnetic field by flux tubes through which energy and particles can be channeled directly to the planet. It is not merely close to the star, it is, magnetically speaking, still inside it. During a flare, these conditions intensify dramatically. The magnetic reconnection event launches a blast wave outward through the stellar wind, compressing the already dense plasma and accelerating it to higher speeds. If a coronal mass ejection accompanies the flare, a wall of magnetized plasma traveling at over 1,000 kilometers per second arrives at the planet's orbital distance within minutes. At that range, the CME has not had space to expand or dissipate. It arrives concentrated. The magnetic field within the CME interacts with whatever planetary magnetic field exists, and if the orientations are unfavorable, the magnetosphere is peeled open. The upper atmosphere is laid bare. Charged particles pour into the atmosphere from above, while the stellar wind hammers it from the sides. The planet does not experience a storm. It experiences a stripping event. A single flare does not destroy an atmosphere, but Proxima Centauri does not deliver a single flare. It delivers 9 per hour, more than 200 per day, more than 80,000 per year. Over the roughly 4.85 billion years that Proxima has existed, the cumulative number of flare events is a number so large that writing it out would fill an entire line of text. The erosion is not a single blow, it is a sandstorm. A continuous, unceasing sandstorm of radiation and particles that has been scouring the nearest planet for longer than multicellular life has existed on Earth, and the superflares add punctuation to the storm. The 2019 event, 100 times more powerful than a typical solar flare, delivered its energy to everything within range in a matter of seconds. At Proxima B's distance, the ultraviolet flux during that event would have been sufficient to drive massive atmospheric loss in a single episode if the planet had any atmosphere to lose. But superflares of that magnitude are estimated to occur multiple times per year. Each one is a hammer blow. Each one strips more material. Each one pushes any surviving atmosphere closer to the threshold beyond which it cannot recover. The specific atmospheric damage has been modeled in detail, and the results are not ambiguous. The Evryscope team's models, later reinforced by studies using the TESS and ALMA data, showed that the repeated flaring could deplete the ozone layer of an Earth-like atmosphere by 90% within 5 years. Not 90% over billions of years, 90% in 5 years. Complete ozone depletion, the total destruction of the ultraviolet shield that makes surface life possible on Earth, could occur within several 100,000 years of sustained flare bombardment. For a star that has been flaring for nearly 5 billion years, several 100,000 years is a rounding error. Without ozone, ultraviolet radiation from the star reaches the planetary surface unfiltered. The UV environment at the surface of a planet around Proxima Centauri, even during quiet periods, would exceed the tolerance of the hardiest known extremophile organisms on Earth. During a superflare, the surface UV dose would spike to sterilizing levels, lethal not just to complex organisms, but to the kind of simple single-celled life that thrives in Earth's most extreme environments. The surface of such a planet would be actively incompatible with the biochemistry that life as we know it depends on, but the damage extends beyond ozone destruction. The same radiation that strips ozone also breaks apart water molecules in the upper atmosphere through photodissociation. Water vapor is split into hydrogen and oxygen. The hydrogen, being the lightest element, escapes to space most readily. The oxygen either escapes more slowly, reacts with surface minerals, or accumulates in the atmosphere. Over billions of years, this process can strip a planet of its entire water inventory. Models suggest that if Proxima b started with an Earth-like quantity of water, the cumulative effect of photodissociation and hydrogen escape could have removed that water entirely within the first billion years or less. This creates a paradox that sits at the heart of the Proxima Centauri story. The planet is in the habitable zone. The habitable zone is defined by the presence of conditions suitable for liquid water. But the same proximity that places the planet in the habitable zone also subjects it to radiation levels that destroy water. The concept of habitability, as applied to this system, contains its own negation. The zone is habitable only in the narrowest thermal sense. Radiatively, magnetically, and chemically, it is a killing field. There is one additional mechanism of damage that the ALMA observations have brought into sharper focus. When the millimeter wavelength data revealed that flaring is far more frequent than optical observations suggested, it also implied that the flux of stellar energetic particles is correspondingly higher. These particles are not just atmospheric erosion agents, they are chemistry disruptors. When high-energy protons collide with atmospheric nitrogen molecules, they produce nitrogen oxide compounds. Nitrogen oxides are potent catalysts for ozone destruction, far more efficient at breaking ozone apart than ultraviolet radiation alone. The continuous injection of nitrogen oxides into a planet's atmosphere by a constant stream of stellar energetic particles would create a chemical environment in which ozone cannot form, even if the other conditions for its production are met. The atmosphere is not just being stripped from the outside, it is being poisoned from within. McGregor framed the central question of the 2025 study with precision. She asked what these flares are doing to the atmospheres of Proxima's planets. She asked whether the flux of radiation and particles is large enough to chemically modify or perhaps completely erode those atmospheres. The answer from the data is that both outcomes are not only possible but likely. Chemical modification and complete erosion are not competing hypotheses. They are sequential stages of the same process. First, the chemistry is disrupted. Then, the atmosphere is stripped. The flares do not choose one mechanism of destruction. They employ all of them simultaneously. The ALMA study also revealed significant asymmetry in the most energetic flares, with the decay phase lasting much longer than the initial burst. This means that after the peak of a powerful flare, the energy release does not simply stop, it tapers gradually, continuing to deliver radiation and accelerated particles over a period that can extend well beyond the initial eruption. For a planet at close range, this extended decay means the exposure duration for each flare event is longer than the burst itself suggests. The planet is not hit by a single flash. It is hit by a flash, followed by a sustained glow that prolongs the damage. And the flares do not arrive alone. They arrive in groups. The test data showed that most of Proxima Centauri's flares appear in clusters rather than as isolated events. A magnetic reconnection in one region of the stellar surface can destabilize adjacent regions, triggering sympathetic flares in rapid succession. The result is not a single burst, but a barrage, a series of eruptions that can sustain elevated radiation levels over hours. During such episodes, the radiation environment at Proxima B's distance would remain in a sustained state of bombardment, with one flare bleeding into the next before the atmosphere has any opportunity to recover. This clustering behavior connects to a broader truth about Proxima Centauri that the ALMA data has crystallized. The star does not alternate between quiet periods and active periods the way the Sun does. The Sun has a clear activity cycle. Solar minimum is genuinely quiet. Flares are rare. The solar wind is calm. Proxima Centauri does not have this luxury of quiet intervals. Its fully convective interior generates magnetic field energy continuously and releases it continuously. The flares are not interruptions in an otherwise calm existence. They are the existence. The baseline state of Proxima Centauri is eruption. There is a sentence from the 2021 study that captures this reality with uncomfortable clarity. McGregor noted that Proxima Centauri's planets are getting hit by events like the 2019 superflare, not once in a century, but at least once a day, if not several times a day. Once a day, every day. For billions of years, the human mind is not equipped to process the scale of that bombardment. We can understand a single hurricane. We can understand a series of storms. We struggle to comprehend a world where the storm never stops, where the concept of calm weather does not exist, where the sky has been screaming since before life on Earth crawled out of the ocean. This is Proxima Centauri, as the instruments see it, not a quiet red dot in the southern sky, not a gentle neighbor waiting to be visited, a machine that converts magnetic energy into particle storms and radiation bursts with a regularity and intensity that no sun-like star can match, aimed at a habitable zone so close to the source that proximity itself becomes the mechanism of destruction. The question that remains is not whether this environment is hostile. The data has settled that. The question is what this hostility means, not just for Proxima b, not just for the Alpha Centauri system, but for the broader assumptions that humanity has built around the idea that the nearest star should also be the most promising destination. Because Proxima Centauri is not an anomaly among red dwarfs. It is typical of them, and red dwarfs make up roughly 70% of all stars in the Milky Way. If the nearest star is this hostile, what does that say about the galaxy we live in? What does that say about the probability that habitable worlds exist, around the most common type of star in the universe. And what does that say about the dream of reaching the stars when the first one we aimed for turns out to be a place that punishes proximity with violence? Those questions are where the answers get uncomfortable. There is a thought experiment that astronomers sometimes use when they talk about the search for habitable worlds, and it goes like this. Imagine you are stranded in a desert. You have been walking for days. Your water is gone. Your body is failing. And then you see it on the horizon, a building, a structure, something that looks like shelter. It is the closest thing to salvation you have ever seen. You gather whatever strength remains and you walk toward it. Every step costs you something you cannot get back. But the building is there. You can see it. It is close. And because it is close, you believe it will save you. You reach the door. You push it open. And inside, you find not water, not shade, not safety, but a furnace. The building is an oven. The closest structure in the desert is the one place that will kill you faster than the desert itself. This is not a perfect analogy. Analogies never are. But it captures something essential about what Proxima Centauri represents in the story of human ambition beyond Earth. The nearest star is not a refuge. It is not a waypoint. It is not a stepping stone towards some grander galactic future. It is a hostile environment wrapped in the illusion of accessibility, and the illusion works precisely because the star is close. Closeness is what makes us look. Closeness is what makes us hope. And closeness is what makes the disappointment cut so deep when the data comes back and tells us that the first destination we dreamed of reaching may be one of the least forgiving places we could possibly aim for. But Proxima Centauri's hostility is not just a local problem. It is not just a story about one star and one planet. It is a story about the most common type of star in the galaxy and what the behavior of that type means for the distribution of habitable worlds across the entire Milky Way. Red dwarfs account for roughly 70% of all stars in the galaxy. Some estimates push that figure closer to 75%. They are everywhere. They are the default star. When you look at the night sky and see the vast dark spaces between the bright points of light, those spaces are not empty. They are filled with red dwarfs, too dim to see, too faint to register on the human retina, but present in numbers that dwarf every other stellar type combined. There are estimated to be between 150 billion and 200 billion red dwarfs in the Milky Way alone. If you picked a star at random from the galactic population, the overwhelming probability is that you would pick a red dwarf. And here is the fact that connects Proxima Centauri's story to the rest of the galaxy. Proxima is not unusual for a red dwarf. It is typical. Its mass, its luminosity, its fully convective interior, its magnetic activity, its flare rate, all of these properties fall within the normal range for M-dwarf stars of similar spectral type. The mechanisms that drive its behavior, the fully convective dynamo, the tangled, pervasive magnetic field, the relentless flare production, are not unique to Proxima. They are inherent to the physics of low-mass stellar interiors. Every fully convective red dwarf in the galaxy operates under the same fundamental constraints. Every one of them generates magnetic fields through the same turbulent process. Every one of them produces flares. Every one of them delivers extreme ultraviolet radiation, X-rays, and stellar energetic particles to any planet orbiting within its habitable zone. This means that the habitability problems identified at Proxima Centauri are not isolated to one system. They are systemic. They apply, with varying degrees of severity, to the habitable zones of the majority of stars in the galaxy. The tidal locking problem is universal for red dwarf habitable zones because the zone is always close to the star. The atmospheric erosion problem is universal because every red dwarf produces a stellar wind and radiation environment that assaults nearby planets. The pre-main sequence water loss problem is universal because every red dwarf contracts slowly and subjects its inner planets to a prolonged period of excessive luminosity before settling onto the main sequence. The flare problem is universal because every fully convective red dwarf sustains magnetic activity for billions of years without the gradual calming that sun-like stars undergo. When the TRAPPIST-1 system was discovered in 2017, with 7 roughly Earth-sized planets orbiting an ultra-cool red dwarf roughly 40 light-years away, the excitement was enormous. 3 of those planets sit within the habitable zone, but TRAPPIST-1 is an M8 dwarf, even smaller and cooler than Proxima Centauri. Its habitable zone is even closer to the star. Its planets are even more tightly packed, even more certainly tidally locked, and even more exposed to the stellar environment. The same problems that plague Proxima b apply to the TRAPPIST-1 system with equal or greater force. The pattern repeats across the catalogue of known exoplanets: Teegarden's star, Ross 128, Wolf 1061, LHS 1140, GJ 1061. Every red dwarf system that has been identified as hosting potentially habitable planets carries the same structural liability. The habitable zone is close, the star is active, the planets are locked. The radiation is intense, the atmospheres are vulnerable. Each system has been individually celebrated as a potential home for life, and each system carries the same fundamental contradiction. The thermal conditions permit liquid water. The radiative and magnetic conditions work to destroy it. This does not mean that life is impossible around red dwarfs. The scientific community has not reached that conclusion, and it would be irresponsible to state it as fact. There are scenarios in which life might persist. A planet with a strong magnetic field, perhaps maintained by vigorous internal convection, driven by tidal heating rather than rotation, could deflect enough of the stellar wind to retain an atmosphere. A planet with a massive initial water inventory could lose enormous quantities to photodissociation and still retain enough to fill oceans. A planet with a thick hydrogen or nitrogen-dominated atmosphere could provide enough shielding to protect the surface from ultraviolet radiation, even without an ozone layer. Subsurface life, organisms living beneath rock or ice, would be largely immune to surface radiation and could theoretically persist indefinitely, regardless of what the star was doing above. These scenarios are scientifically legitimate. They are explored in peer-reviewed literature. They represent real possibilities that deserve continued investigation. But they are also, every one of them, a retreat from the original hope. The original hope was that Proxima b might be Earth-like, that it might have blue skies and open water and breathable air, that it might be a place where human beings could, someday, stand on the surface and look up at a different star. Every survivable scenario that has been proposed for Proxima b requires the planet to be profoundly unlike Earth. An ocean world with no land, a planet buried under a thick hydrogen envelope, a frozen surface with life hiding in subsurface caverns. These are not destinations for human ambition. They are places where life might endure in forms so alien to our experience that finding them would tell us more about the resilience of biology than about the prospects for human expansion. And this is where the story shifts from astrophysics to something deeper, because the significance of Proxima Centauri is not ultimately about one planet's atmosphere or one star's flare rate. It is about what the nearest star teaches us about the relationship between proximity and promise, between distance and danger, between the human instinct to reach for what is close and the universe's indifference to that instinct. Human beings are proximity creatures. Our entire evolutionary history has been shaped by the principle that closer is better. The nearest water source is the one you drink from. The nearest shelter is the one you sleep in. The nearest territory is the one you explore first. This principle is so deeply embedded in human cognition that it operates below the level of conscious thought. When we learned that the nearest star had a planet in the habitable zone, the response was not rational calculation, it was reflex. The nearest habitable world. Of course, we should go there. Of course, it should be our first destination. Of course, it must hold some promise. It is the closest one. But the universe does not organize itself according to human convenience. The nearest star is not the nearest star because it is suitable. It is the nearest star because of the random geometry of stellar orbits in the solar neighborhood. Its proximity carries no information about its character. Distance tells you how far you have to travel. It tells you nothing about what you will find when you arrive. Proxima Centauri is teaching us this lesson in the hardest possible way. It sat in the sky for a century, invisible, unnamed, unremarkable. Then we discovered it was close. Then we discovered it had a planet. Then we discovered the planet was in the habitable zone. Each revelation added another layer of hope, another reason to believe that the universe had placed something wonderful right on our doorstep. And then the data started coming in. The flares, the radiation, the stellar wind, the tidal locking, the pre-main sequence water loss, the ALMA observations. 463 flares in 50 hours. Each data point peeled back one layer of the illusion and revealed something harder, colder, and more indifferent than the hope it replaced. Consider for a moment what it would actually mean to send a probe to Proxima Centauri. The breakthrough starshot concept envisions accelerating gram-scale spacecraft to 20% of the speed of light using a ground-based laser array. If the engineering challenges could be solved, a probe could reach the Proxima Centauri system in approximately 20 years. It would arrive traveling at 60,000 kilometers per second. At that speed, the probe would pass through the entire system in a matter of hours. It would have a brief window to collect data before sailing onward into the interstellar void, never to return. What would it find? Based on everything the instruments have told us, the most likely scenario is this: a dim red star, visually unremarkable, hanging in a sky far from any familiar constellation. A planet, possibly rocky, possibly slightly larger than Earth, locked in a permanent stare at its star. One hemisphere bathed in dull red light, the other in eternal darkness. No blue sky. No breathable air. Possibly no atmosphere at all. A surface that, if exposed, would be bombarded by ultraviolet radiation and high-energy particles at levels incompatible with any known form of surface biology. A world that might once have had water, but almost certainly lost it billions of years ago to the relentless photodissociation driven by a star that never learned to calm down. And in the background, every few minutes, a flash. A tiny brightening of the star as another magnetic reconnection event tears through the corona, sending another burst of particles and radiation into the space where the planet orbits. Not a dramatic explosion visible to the probe's cameras, a subtle pulse detectable only in the instruments, but continuous, unceasing. A heartbeat of destruction that has been running for 5 billion years and will continue for trillions more. The probe would record this data. It would transmit it back to Earth using its tiny onboard laser, a signal so faint that it would take the largest receiving arrays on the planet to detect it. The data would travel at the speed of light, arriving 4.24 years after transmission. And when the scientists on Earth decoded the signal and analyzed the results, they would find confirmation of what the ground-based and space-based instruments had already suggested. The nearest star is not a destination, it is a warning. This is not the ending that the Proxima Centauri story was supposed to have. When the planet was discovered in 2016, the narrative was forward-looking and optimistic. Humanity had found a target. The nearest potentially habitable world. The story was supposed to go from discovery to exploration to arrival to wonder. Instead, the story has gone from discovery to investigation to a slow, methodical accumulation of evidence that the target is not what we imagined. The wonder has not disappeared. The science is still extraordinary. Understanding Proxima Centauri's flare behavior, atmospheric erosion mechanisms, and stellar wind environment is advancing our knowledge of stellar physics, planetary science, and the conditions for habitability in ways that will inform the search for life for decades to come. The ALMA data alone represents a landmark in our understanding of Dwarf activity. The science is magnificent. But the dream has changed shape. The nearest star was supposed to be the first page of an interstellar story. It is beginning to look more like a cautionary tale, a lesson in the difference between what we wish the universe to be and what the universe actually is. And perhaps the most unsettling dimension of this lesson is not the hostility itself, but what it says about the broader landscape of potentially habitable worlds. If 70% of stars in the galaxy are red dwarfs, and if the habitable zones of red dwarfs are systematically hostile to the retention of atmospheres and surface water, then the number of genuinely habitable planets in the Milky Way may be far smaller than optimistic estimates suggest. The Drake equation includes a term for the fraction of planets where life actually appears. But before life can appear, the planet needs to retain the basic prerequisites: an atmosphere, liquid water, protection from sterilizing radiation, for long enough that the chemistry of life can get started. Around red dwarfs, those prerequisites are under constant assault. The fraction of red dwarf planets that clear this bar may be very small. This does not mean that habitable worlds do not exist. It means they may be concentrated around the minority of stars that are not red dwarfs, G-type stars like our Sun, K-type stars, slightly cooler and longer-lived than the Sun, but with habitable zones far enough from the surface to avoid the worst effects of tidal locking and close-range radiation. These stars make up perhaps 20 to 25% of the galactic population. Their habitable zones are more distant, their radiation environments more moderate, their activity cycles more likely to include long periods of calm during which planetary atmospheres can stabilize and recover. If habitable worlds are primarily found around these stars rather than around red dwarfs, then the geography of life in the galaxy is very different from what many researchers assumed. Life would not be scattered across the majority of stellar systems. It would be concentrated in a minority, an archipelago of calm harbors in a galaxy dominated by stormy seas. And the nearest members of that minority are not as close as Proxima Centauri. Alpha Centauri A, a G-type star with properties similar to the Sun, is part of the same triple system, sitting at 4.37 light-years away. In August of 2024, the James Webb Space Telescope detected a thermal signature consistent with a possible giant planet orbiting Alpha Centauri A, though follow-up observations in early 2025 did not redetect the signal, creating a mystery that remains unresolved. If a planet does exist there, the environment around Alpha Centauri A would be profoundly different from the environment around Proxima. The habitable zone would be farther from the star. Tidal locking would be unlikely, the stellar wind would be moderate, the flare rate would be low, the radiation environment would be manageable. It would be, in short, the kind of place where the word habitable means something real. But Alpha Centauri A is a binary companion to Alpha Centauri B, and the gravitational dynamics of binary systems can complicate planetary stability in ways that are still being studied. The nearest single Sun-like star is farther still. And every additional light year of distance is another barrier to exploration, another multiplier on the travel time, another reduction in the feasibility of sending probes, let alone people. This is the cruelty of proximity. The universe placed the closest star within what feels like reaching distance and then made it hostile. It placed the more promising stars slightly farther away, just beyond the edge of what our most ambitious engineering concepts can currently target. The galaxy is not arranged for human convenience. It is arranged according to the physics of stellar formation and orbital mechanics, and those physics do not care about our hopes. There is a tendency, when confronted with a story like this, to reach for reassurance, to say that the science is not settled, that future observations might reveal surprises, that Proxima b might turn out to be habitable after all. And it is true that the science is not settled. It is true that we do not have direct observations of Proxima b's atmosphere. It is true that future telescopes may reveal something unexpected. Science is a process of continuous revision, and certainty is a luxury it rarely offers. But intellectual honesty requires acknowledging where the weight of evidence currently sits, and the weight of evidence sits heavily against the habitability of Proxima b, not because of one study, not because of one data point, but because of the convergence of multiple independent lines of evidence, each pointing in the same direction. The fully convective interior sustaining magnetic activity for billions of years, the flare rate, now quantified at millimeter wavelengths, revealing activity far more frequent than optical data alone suggested. The radiation environment, measured across multiple wavelengths, showing extreme ultraviolet and X-ray doses that are orders of magnitude beyond what Earth receives. The stellar wind, modeled in three-dimensional magnetohydrodynamic simulations, showing pressures that compress any plausible magnetosphere to the breaking point. The pre-main sequence evolution, showing a prolonged period during which the planet's water could have been irreversibly lost. The tidal locking, undermining the generation of a protective magnetic field. Each of these lines of evidence is independent. Each has been developed by separate research teams using different methods. And they all point to the same conclusion. The nearest star to Earth hosts a habitable zone that is, by every measure we currently have, one of the most punishing environments in the solar neighborhood. There is one final thought that belongs here, and it is not about Proxima Centauri specifically. It is about what this story reveals about the act of looking outward. When humanity first pointed radio telescopes at the sky and began listening for signals from other civilizations, there was an implicit assumption embedded in the project. The assumption was that the universe was a place where intelligence could take root and flourish, where habitable conditions were common enough that other minds had arisen and might be trying to communicate. The search for extraterrestrial intelligence was built on optimism, on the idea that the cosmos is, if not welcoming, at least permissive, that the default state of a planet in a habitable zone is something approaching livable. Proxima Centauri challenges that assumption at its foundation. It suggests that the most common type of star in the galaxy may be structurally hostile to the retention of habitable conditions on nearby planets. It suggests that the concept of a habitable zone, as defined purely by temperature, is dangerously incomplete. A zone where liquid water could exist thermally, but where the atmosphere is being continuously stripped, the ozone is being continuously destroyed, and the surface is being continuously irradiated, is not habitable in any meaningful biological sense. The word habitable, applied to such a zone, is not a description of reality. It is a description of one narrow parameter that ignores every other parameter that matters. If the majority of stars in the galaxy create this kind of environment in their habitable zones, then the number of truly habitable worlds may be far smaller than the optimistic estimates of the last few decades have suggested. The galaxy may not be a garden with life scattered on every suitable world. It may be a desert with rare oases, separated by vast stretches of hostile emptiness, and the oases may be found only around the minority of stars that burn gently enough and maintain enough distance from their planets to allow the fragile chemistry of life a chance to operate. This is not a cause for despair, it is a cause for precision, for understanding the universe as it is rather than as we wish it to be. For recognizing that the search for habitable worlds requires not just finding planets in the right temperature range, but understanding the full electromagnetic, magnetic, and particle environment those planets are embedded in. For accepting that the nearest star may not be the best star, that the first destination may not be the right destination, and that the dream of reaching another world requires not just engineering brilliance, but the wisdom to choose a target that will not punish us for arriving. Proxima Centauri is still there. It will always be there. 4.24 light-years away, too dim to see with the naked eye, quietly flaring in the southern sky, delivering its relentless radiation to everything in its vicinity. It will outlive our sun. It will outlive every sun-like star in the galaxy. It will still be burning, still flaring, still punishing its habitable zone trillions of years from now, long after every star you can see tonight has gone dark. And the planet will still be there too, if it exists as we believe it does, locked in its eternal stare, one face lit by dim red light, the other in permanent shadow. No sky, no seasons, no dawn. Just the steady, crushing proximity of a star that never stops. A world close enough to dream about and hostile enough to punish the dream. The nearest star is not what we hoped it would be. It is what it is. A lesson written in plasma and magnetic fields and 463 flares in 50 hours. A reminder that the universe does not owe us a friendly neighbor. That nearness is not kindness. That the closest light in the dark may be the one you should not walk toward. The instruments are still running. The data is still coming in, and every new measurement tells the same story. The most dangerous star near Earth is not the largest or the brightest or the most dramatic. It is the smallest, the dimmest, the closest, the one we aimed for first, the one that was always right there, waiting with a patience that only a star that will burn for trillions of years can afford, to teach us that proximity is the cruelest illusion the cosmos has to offer.